Okay. So I didn't erase the questions. That's all right. We can still kind of see it. First question on the table H there, number 7. If atmospheric pressure is increased to 120, what is the boiling point of water, Mariana? 105 degrees Celsius. Let's find out. So if we increase from 101.3 up to 120, so this is 110, 120, we go over to water and then drop straight down, 105. Very good. 105 degrees Celsius. Good job. Air pressure goes up, boiling point goes up because you need more energy for the vapor pressure to equal the air pressure. 8. If atmospheric pressure is decreased to 50, what is the boiling point of ethanol? Earl?
62 degrees Celsius.
62. Let's find out. We drop the dotted line to 50. We go to ethanol, which is here, and 55, 62, you said? Yeah, 62. Good job. 62 degrees. Again, drop the air pressure. You need less energy, right? Less vapor pressure pushing up because there's less air pressure pushing down. Therefore, the boiling point goes down. All right, 9. At what temp does ethanoic acid have a vapor pressure of 80 kPa? Go ahead, Shane. 110 degrees Celsius. Let's see here. If we go to 110 and we go up to ethanoic acid, that should be about an 80 there. Let's see, 670, 80. Very good. Yep, very good. Good job. 10. What temperature does water have the same vapor pressure as ethanol does at 83? 73, 74. So how would I figure this one out?
Go to 83.
Go to 83 degrees, so 80, 85, so right about here.
Yeah. And then, and then go up to the line.
Ethanol?
Yeah.
Yeah, or wait, where's ethanol? Right here? Hold on,
Whoops.
I lost my train of thought here. 80, so 83, we go up to ethanol.
Oh, I did ethanolic acid.
All right, I just did the same thing. All right, let's do it now.
And then go over to where it is the same pressure as water.
Right, and then drop back down?
Yeah.
Yep, good. So we go down here, and I'm gonna say, what do you think? Just past 100 there?
Yeah.
So 102, 103 degrees Celsius, 102, 103. We're good? Okay, so when you have that cumulative test down the road here before the end of the quarter, stuff like this will be on. Okay, so that's why we're practicing that. So you could keep those sheets if you want, if you like keeping worksheets to review from. That's good, I think that's a good idea, but if not, you can just recycle it at some point, just not right now, just hang on to that. All right, let's go over the 3 questions on the board. All right, so how many liters of space does 1 mole of gas occupy at STP? Morgan? 22.4 liters, that is a constant. So we're going to use that number a little bit here today and tomorrow. Okay? Very good, that is a constant. Any gas, right? So there's that mole box over here. So I'll get this thing out. The analogy here with this mole box is that we say, all right, was that lab or was that class that Ryan was messing with that?
Lab.
That was really funny. So yeah, it's really cheesy, but I like it because it's colorful. And I obviously made it. You can actually buy this. They sell this online for like, I don't even know, like 30 bucks or some ridiculous thing. So it literally is, it's just a box with all these numbers written on them. So I figured just make my own for free. So the analogy is inside this box is 1 mole of a gas, and I say it's 1 mole of CO2. 1 mole of CO2. And then on the side here, we have at STP, 0, 1 ATM, 0 Celsius, 1 ATM, 273 K, and 101.3. STP. This is only true at STP. Why? You start changing temperature and pressure, what happens to gases? You start changing temperature and pressure on gases. What do they do? I expected an answer a lot faster than that. You start changing the temperature that a gas exists at. So you heat it up or cool it down, or you put it under more pressure or less pressure. What happens to gases if you heat them up or cool them down? Either one. Right, they expand or they contract or they get compressed. So therefore it won't be taking up that much space, right? So if we start changing those numbers and it's not 0 Celsius, it's not 1 ATM, then it's not going to take up 22.4. So that's really important. It has to be at the same temperature and pressure. The other thing that we're going to learn today is what is a mole. I'm not going to spend a ton of time on it, but a little bit because it plays into this. But we're going to kind of do both of these at the same time using table I. So there's a bunch of stuff we're going to be learning today, and then we'll go over it again tomorrow. So between today and tomorrow, you guys should be good with that. But we are going to revisit the mole down the road. So I'm going to intro it just so you have a rough idea, and then we'll deal with it more down the road. But anyways, so we say inside this box is a mole of CO2. So 1 mole of CO2 occupies 22.4 liters of space, right? So this is a constant. That's the point of this box. Who remembers how many particles are in 1 mole? That's why mole day was mole day. Avogadro's number. Marcy.
6.022 times 10 to the 23rd.
Very good. 6.022 times 10 to the 23rd. That's how many particles are inside this box, right? It's an analogy. So we say, all right, we have 1 mole. What does that mean? It takes up that much space. Bless you. Who was that? Emma? Bless you. It takes up that much space, and that means there's that many particles inside the box. But again, all of this takes place at STP. It's important to understand. The last thing about this box that kind of answers this question, sort of. So let's answer it first, then we'll come back to the box. What is a mole? You saw that mole day video. I just kind of explained it again a little bit.
It's an amount of substance.
Yeah, it's the amount of a substance. And how much is it? That's what a mole is. But the mass of a substance also plays a role. So if I have 1 mole of CO2, I have this many particles of CO2. If I have 1 mole of sulfur, then I would have this many particles of sulfur. So this number is a constant. But if you look over there, the masses of all of them change. This is something I want you to start understanding today. That even though you have the same number of particles, the mass changes, which should make sense to you. If I had this many particles of lead versus this many particles of air, which would weigh more? The lead. Everybody knows that. You just know it. Maybe you don't know why you know it, but you know it. Maybe someone could explain. Why, if we have the same number of particles of one thing and something else, their weight or their mass might be different? Anybody? So if I'm holding 1 particle of lead and 1 particle of CO2, lead's going to be more mass, right? A larger mass. Why? It's more dense. Very good, Slade. It's more dense. So, this box, we say, contains 44 grams of CO2. Where's that 44 coming from? Who can do the math? Who's following me? Who's picking up what I'm putting down? Earl.
27. No, never mind.
Okay. Good try. Where's the 44 come from? Say it again. What's both of them mean? There's 2 oxygens, right? Yeah. It's the mass of 1 carbon and 2 oxygens added together. What's the mass of carbon? Over there. 12. 12 grams. What's the mass of oxygen? 16. What's 16 plus 16? 32. So that's the 2 oxygens. Okay, that's the 2 oxygens. What's 32 plus 12? 44. So you just learned something really important that I want you to start to essentially memorize and understand starting right now. The mass of the elements on the chart is equivalent to 1 mole. The mass of the element on the chart is equivalent to 1 mole. Again, this is just an intro. We're going to focus more on this down the road, but I need to introduce it to do what we're doing today. So this formula is CO2, and this formula means 1 carbon and 2 oxygens, so that's a mass of 44. So if I, instead of a mole of CO2, let's say I had a mole of water in here. How much would it weigh? That's a bad way to say it. What would the mass be? What would the mass be if I had 1 mole of water? Raise your hands. If this was filled with 1 mole of water. So right now we're saying this has a mass of 44 grams. What if this was a mole of water? Same number of particles, okay? And if it was water vapor, same amount of space, liters, but this would change. That would change. What would be the mass of 1 mole of water?
10.
You're almost there. It's a little bit heavier. You're almost there. Emily. 18. 1 mole of water. This is how we figure it out. Oh, what am I doing? That's supposed to be an H. H2O. the mass on the chart is equal to 1 mole. What is the mole? It's this, 6.022 times 10 to the 23rd particles. So what's the mass of each hydrogen? 1. So that's 1 plus 1. There's 2 of them. What's the mass of oxygen? 16. That equals 18 grams. So do I expect you to just get it and you're good and you know moles now? No. But it's an introduction to start understanding how the mass up there plays a role when we talk about moles. Okay? Last thing, I'll leave you with this, and then we'll talk about endo-exo. I got 2 demos to show you about this, and then we'll talk about table I. The unit on the mass. So hydrogen is 1, oxygen is 16, carbon is 12. The unit, see if this makes sense to you. The unit, so oxygen has a mass of 16 grams per mole. Why does that unit, grams per mole, make sense? Based on what I just went over. How come it's not just grams? Why is it grams per mole? Laura?
Because the mass of that element is equal.
Very good. The mass of the elements is equal to 1 mole. So if you have 16 grams, you're holding 16 grams of oxygen. I know that's weird, it's a gas. But if you're holding 16 grams of oxygen, you're holding 1 mole of oxygen. That's how many grams are in 1 mole, grams per mole. Some of you have probably heard this term. This is called the molar mass of oxygen. It's also called the gram formula mass of oxygen. So again, I'm kind of going over a whole bunch of new stuff here. You don't need to know it all right now, right this second, but I'm just kind of getting the ball rolling with the concept of what a mole is and then how the masses play a role with that. Okay? So the unit, grams per mole, that's the mass from the chart, and the mass of any compound is always equal to 1 mole. Or element. So we'll talk more about that down the road in a little bit more today about what a mole is, because that's important. What about exo and endo? We'll put the mole box aside. What's exo and endo mean? Laura, give me one of them.
Exothermic releases heat.
Exothermic releases heat. Very good. Any process that releases heat is called exothermic. Good job. What about endothermic, Michaela? Yeah, takes in, absorbs, gains heat, whatever word you want to use. I tend to say exothermic releases heat and endothermic absorbs heat. That's how I tend to word it. But basically, exothermic means get rid of the heat, and then endothermic means you're gaining it, taking it in, absorbing, whatever word you want to use. Okay? Now, go to table I. Please, take that out. Table I says on top there, you might as well take your notes out too, if they're not out already. Just want to make sure I'm not forgetting about solids here. I think we covered everything. Okay, so table I, what's the title? Laura Griffin. Title of table I. Good. Heats of reaction at 101.3 kPa. What's that? Standard pressure. 298 K. Not standard temperature. You know what that's called? Normal temperature. So you have normal, which is 25 Celsius, and standard, which is 0 Celsius. Normal, 298 K. Standard, 273 K. Yeah, it's kind of weird, kind of confusing, but it is what it is. So what is this chart showing? What is it giving us? What information? The heats of reaction. What do you guys think that means? Heats of reaction. What do you think that means? Hannah, any thought there? Heats of reaction? Or, you're right. Good, that's the same thing. Makes heat, gives off heat, or what else can it do? It was the last question we just went over. So it can either release the heat, that's exothermic, or absorb the heat. There's only 2 things that could ever happen in a chemical reaction or a physical process. It can give off heat, or it can absorb heat. So release it or absorb it. Table I shows us that. Look in the top right corner of table I. See the delta H, parentheses, Kj. That stands for kilojoules. Joules is a unit for energy. Delta H stands for, any idea? What do you think the H stands for? Earl. Heat. What's delta stand for? Change, yes. Change in heat. So if you look at that first reaction, CH4 plus 2O2 yields CO2 plus 2H2O. That's a chemical equation for a combustion reaction, actually. There is a change of 890.4, but there's a negative in front of it. Negative numbers don't exist in chemistry, so why is it written there?
It says at the bottom it indicates an exothermic reaction.
Whoa, whoa, whoa. Emily's reading ahead. Wow. Emily, overachiever you. Good job. Good job. Yes, that was going exactly. That's what my next question was. You guys can answer the question. I don't need to answer that. Why is there a negative? Look at the bottom. Very good, Emily. The delta H values are based on molar quantities represented in the equation. Notice how it said molar quantity. What does that mean? Moles. That's why I want to kind of intro it today. A minus sign indicates an exothermic reaction, which means what if it's exothermic? It gives off heat. So if we look at that first reaction again, that chemical equation, when it occurs, gives off 890.4 kilojoules of heat. The negative sign is not really part of the number. It's just to let you know it's giving off the heat. So, who thinks they're logical? What does a positive sign mean? Look about halfway down-ish. See that one that says positive 182.6? What do you guys think that means? Mackenzie?
Absorbing.
Yeah, it absorbs heat, which is what type of reaction? Endothermic. Bless you. Now we're going to write all this down, but I wanted to kind of talk about it out loud and look at the chart first. So this is a really important table, and it's really important for you to be able to find reactions and know, do they release heat or absorb heat? How do you know that? Look at the sign on the delta H, which is the change in the heat. Again, we will write all this down. So anytime you see a negative, it's releasing heat. Anytime you see a positive, it's absorbing or gaining, and that's endothermic. The negative means exothermic. But it says it right on the bottom, right? So you don't have to memorize that, even though you probably will. All right? So now what I want to do is bring you guys back. Grab your glasses. I got a pretty cool demo.